Okay, so far we've talked about um, ideal solutions. So now I'd like to spend a little time talking about um, non-ideal and regular solutions. So one concept or way of approaching a non-ideal solution is to realize that Raoult's law, which we said is the law that's followed by ideal solutions, only generally applies or only typically applies at very high concentration. So when the material is very close to pure. And so it turns out that there's another linear relation that tends to be obeyed in dilute concentration. So Henry's law often applies in the dilute limit. And Henry's law just states that the partial pressure of some component B is equal to some constant, which we'll call Kb, times the mole fraction of B. That is, it's linear in the mole fraction of B. And so what does this imply? Well, it implies that if we make a graph of pressure, so let's make this is our pressure, and this is our concentration, let's say concentration of some species B, so here we're pure B, and here we're pure A, then if we look at the pure phase, we know that the pressure, partial pressure of the pure phase has to be PB star, right? And so, and then near pure phase, we have Raoultian behavior, so it tends to fall on this straight line that would join the pure phase to zero. So we have some behavior like this up here, but that, so here we're obeying Raoult's law, but then as we move away, we don't quite follow this behavior all the time, but there's some other linear behavior. Here, let's draw another line here. And we follow basically linear behavior along some other curve down here, and then there's some transition region in the middle. So down here we're following Henry's law, and the intersection here gives us, we see that when Kb equals 1, Pb is equal to Kb, so Kb is the intersection of this extrapolation of this line to see where it hits the xb equals 1 axis. Okay. So a solution that behaves in this way, so if we obey Raoult's law for the solvent, that is, for the majority species, and Henry's law for the solute, that is, the dilute species, then we call that an ideal dilute solution. Just by convention. Okay. Now, in general, right, we might want to have a way of expressing this, right? So there's the concept of an activity, and this is just essentially a convention. And it just says that we know that for any general chemical potential, we can write the chemical potential of, let's say, species A as the chemical potential of pure A plus RT times the natural log of the partial pressure of A over the partial pressure of pure A, right? So that was our general So this is the chemical potential of pure A, and this is the related to the vapor pressure of A, right? So, and we know that for Raoult, right, if we have a Raoultian solution, we said this reduced to mu A is equal to mu A star plus RT natural log of XA. Okay. But in general, that's not the case. So one way to handle this is to say, okay, define the activity of A as A sub A. Okay, and so we're going to say A sub A is equal to the vapor pressure of A over the vapor pressure of pure A, just by definition. And we're going to define an activity coefficient by saying that A sub A is equal to gamma A times XA, where gamma A is the activity coefficient. Right? So if we write it this way, then we can see that, well, in general, mu A is equal to mu A star plus RT natural log of AA, right, which is equal to mu A star plus RT natural log of gamma A XA, right? Or in other words, we have mu A is equal to mu A star plus RT natural log of XA, which would be the ideal solution, plus a correction term, RT natural log of gamma A. Gamma A would, of course, be 1 in the Raoultian case, but in general it's not 1, and this would give the deviation from ideality. Now, of course, all we've done here is rename things. This doesn't tell us anything particularly interesting about the physics, but it does give us the common notation that gets used when discussing solutions. So the next thing we'd like to talk about is how we can relate this quantity mu A to the free energy per mole, which depends on the concentration. Okay, so how do we relate mu A and mu B, if we have a solution of A and B, to the free energy per mole of the system, of the solution? Okay.